All right, folks, it's Bass Action, back in action here. In this video, we are going to talk about geometric sequences and series. That means that we're going to talk about how to write the rule for a geometric sequence, and then we are also going to talk about how to find different sums of geometric sequences and series. So let's first jump into what is a geometric sequence. It's going to be a sequence where the ratio, now remember ratio is just a fancy way of saying fraction. The ratio of each term to its previous term will remain the same, okay? So the little reminder that I want you to have in your head here is that when we're thinking about geometric sequences, that we are thinking about exponential functions. So just like our arithmetic sequences were linear, our geometric sequences are going to be exponential. Now, just like before, we have a little formula here that we can just follow, and we're just going to use this little formula to write our general rules. We're also going to have the ability to find some sums. We had a formula to find the sum of an arithmetic sequence. We're going to have a sum for a geometric. Now, just like before, we can write this using a summation notation, or we can write it just over here and expand the whole actual formula out. The last thing that we're going to look at is this idea of an infinite sum. So we've been working with finite sums up until now. So that would be, let's say, from the first term up until the 7th or the 8th or the 100th, however many terms you might want to add. An infinite sum is going to be what it sounds like. It's going to go from our first term and it's going to go all the way to infinity. Now, the important thing to understand here is that, first of all, the formula is much easier than this formula, but not all formulas, not all geometric sequences will have the ability to have an infinite sum. We're going to have this an idea of a converge or a diverge, okay? If the formula converges, then it will have a sum, okay? So an infinite sum. So only the ones that are going to converge will have an infinite sum, and it will converge if the R value, the ratio, is going to be less than 1, okay? So if we've got an R value that is less than 1, it's going to converge. If it diverges, that means that the ratio is going to be more than 1, and then there will not be a sum. We'll just say that it diverges, and we all understand that means that we can't find the sum. So we're going to reference these formulas as we go through the rest of the video. Now, the first thing that we're going to do is we're going to look at how can we recognize what a geometric sequence looks like, and then we're going to write our general rule. So before, when we were looking for our arithmetic, we were looking to be able to add a number each time and have that number that we add stay the same. Well, we can clearly see we're not adding the same amount, so it's definitely not going to be arithmetic. But what we can notice is if we take this second term, this 6, and put it over 2, creating a ratio of a term over its previous, we can see that that is going to reduce to a nice 3. And if we continue and we take 18 and put it over its previous term, we're going to get a 3 again. And if you did it one more time, we could keep going and keep checking it. We would have 54 over 18, and we would get 3 again. That means that our R value is going to be 3. And of course, for our formula, these are going to be much easier. We only need the R value in the first term. So our general rule is going to be a sub n, and then our first term of 2. And then we're going to have our ratio, our common ratio is what we're going to call that. And we're going to use an n-1 exponent. Now, the next one's a little bit more complicated because I've got these fractions going on here. So the first thing that we're going to do is we're going to check to make sure that our ratio stays the same. So we're going to take 4/3, but instead of doing 4/3 divided by 2, I'm going to think 4/3 times a half, okay? And if I do my 4/3 times a half, and of course I reduce that nice fraction I would get a nice 2/3 here. If I repeat the process and do 8/9, oops, I meant to write a 9 there, sorry. If I do 8/9 divided by 4/3, but again, divided by a fraction looks weird, so we're going to multiply by that reciprocal. And of course, if we reduce that, if you need to see it written out, we can. We can do our 3 goes into our 9, and our 4 goes into our 8, and sure enough, we get that same ratio again of 2/3. You could extend this one more time, do 16/27 times 9/8, and you'd get the same thing. So this is going to be our ratio again. So our rule, a sub n, we need our first term of 2, and then we're going to have our ratio of 2/3, and our exponent is n minus 1. So that's all that we've got. These are much, much easier to write. Now, when we get into writing the rules, if I don't give you the nice little sequence, we're going to need to do a little bit more work. So this one, I've given you the ratio, and that's pretty convenient on this one. So I've given you the ratio, but I did not give you the first term this time. So we'll start this off in a similar way that we did before. So we'll start off with our general rule. We don't know the first term, so we'll write our a sub 1. We do know that our ratio is going to be a -4, and then I can fill in my n minus 1. From here, we're going to use this term that we've got. We know that the sixth term is a -1,536. I still don't know the first term. I do still know that ratio, and now my n value is going to be 6, so I can fill in this 6 minus 1. Now from here, what I'm going to do is I'm going to start to simplify this and clean this up. So I'm going to have my -1,536 and my a sub 1, and my -4 to the 6 minus 1 is really the -4 to the 5th power, okay? And that's going to give me a negative, because remember, my negative to an odd power is still going to be negative 1,024. Now, when I go to solve this, I can immediately see that my negatives are going to cancel out. So I like to get rid of those as soon as I can. So my first term, my a sub 1, is going to be 1,536 divided by 1,024. And then I'm going to need to reduce that fraction. And if you go through that nice reducing process, you'll get a pretty simple looking fraction. And it's important to remember to always reduce, okay? I don't want to see any answers where your fractions have not been reduced. Now, so our ratio is going to be 3, or our first term is going to be 3/2. So we can write our rule of a sub n. We're going to take our first term this time, and then we're going to take our ratio. We want to keep that in the parentheses there, and then our n minus 1. So not too bad. All right, now the next one's going to be a little bit more complicated because now I haven't given you either of the pieces. All I've given you are 2 random terms. So we're going to get our first terms, and I personally like to write this little rule here to remind myself what is the formula that I'm substituting in. It's going to help me keep track of what I'm doing. So I'm going to fill in my 1/3. I don't know my first term. I don't know my ratio, but I do know that my n value is 3. So I'm going to do that in my head now. 3 minus 1 is going to be 2. Okay, so that's going to give me an r squared. Now I'm going to write my second, I'm going to use my second one, and we're going to again say my value is 1/81. I don't know the first term. I don't know the ratio, but I do know that my n value is 6. So I'm going to do 6 minus 1, and that's going to give me r to the 5th. So what I have here is a system of equations, and I need to solve this system. It's going to be the easiest thing to do to solve for this a value right here. So I'm going to rearrange this and say a sub 1. And if I divide by this r squared, I'm essentially multiplying by 1/r². So that left side will become 1/3r². Now I can take this value expression for a sub 1 and I can substitute it in right here. So I'm going to have my 1/81, and then I'm going to have my 1/3r² times r to the 5th, and it might be helpful for you to put that 1/1. It'll help you see a little better what's happening. Now, of course, these values can reduce. We know that on our exponent rules, we're going to subtract those exponents. So this is going to become, this one's going to cancel, and this is going to become r³. So now, the problem that we're actually solving, if I go ahead and I multiply both sides by 3, what I end up with here is 1 over 27 equals r cubed. Well, now I can just take the cube root of each side, and I will get an r value of 1/3. So now that I have my r value of 1/3, I can go back to this original little expression back here, and I can say, okay, well, that means that a sub 1 is 1 over 3, and then that's going to get multiplied by that r squared. Okay, so my r squared in this case, I should say, is divided by my r squared. So I'm going to multiply by this reciprocal. Actually, you know what I'm going to do? I'm going to rewrite this. I think this is going to confuse some of you otherwise. So we're going to say, I'm going to put my r squared back over here. So I'm going to have my 1/3 over here squared. And let's clean this up for you a little bit. Okay, now let's take a look at it from this perspective. So I'm actually going to start back here on this problem. My iPad's a little frozen here. I'm going to start back at before I divided by that r squared, because I think that's going to confuse some of you since that ratio does turn out to be. So we're going to start here. Okay, so I've got my r squared here is my 1/3 squared, and then I've got my a1 and then my 1/3. Now this is going to become 1/9. So I have 1/9 a sub 1 equals 1/3. And now it's a little easier to see that what we're going to do is we're going to multiply both sides by 9. So that's going to get me a first term of 3. Okay, so now I can go ahead and I can write my final equation and say, I'm going to write it up here because it got a little messy for you. I'm sorry. A sub n, my first term is 3. My ratio is 1/3, and this is to the n minus 1. So that's going to be our final rule. Sorry, this got a little bit messy, guys. But I think that being able to see how we're handling these fractions here, otherwise we would have had to do 1 over, and we would have had a 3, and then we would have had these fractions in that denominator. That would have been a little confusing. Okay, the last thing we're going to do is we're going to look at finding the sum. Remember, we can find the finite sum. We know that this is a geometric rule, so we're going to follow our formula for our geometric sum. And that formula, I'm going to rewrite it here for you. That formula is going to be a sub 1, and I'm going to put this over 1 because we're going to have some fractions going on here. And we're going to have 1 minus r to the n. That's a common error. Students want to say n minus 1, and 1 minus r. So we're just going to pull our numbers straight from here. So our first term is 2. So I'm going to put a 2 over 1. And then I'm going to have a 1 minus, and notice that my r value is negative. So I want to make sure to put that in parentheses because it does not cancel out with this negative because it has an exponent on it. Since we're going to the 9th term, I'm going to fill in that 9. Then in the denominator, I'm going to do 1 minus my r value. So that's going to be 1 minus a 5, a negative 5. So it's going to become a 1 plus 5. So what I can see is that that's going to be a 2 divided by a 6. So I'm going to clean that part up right away and rewrite that as a 3. Okay, now when I do that, when I clean that up as my 2 there, then I can just type this whole thing into my calculator here. And I'm going to get this is going to turn out to be something negative. Okay, so I'm going to have really a 1 plus a negative 5. So that's going to give me, when I do this 1 minus, this is going to give me something negative. So this is going to flip to something positive when I'm done. And when I type this in my calculator, I'm going to get a final answer of 65,1042. Sorry, not 65,000, 651,042. Sorry, I was reading that from the calculator wrong there. Now, the last thing that we're going to do is we're going to look at these two infinite sums. Notice that these are an infinite. Now, the first thing that we want to notice here is that this r value is greater than 1. And if that r value is greater than 1, we are simply going to say that this diverges. And if it diverges, there's not going to be a sum, so we can just skip it and move on. So when it says find the sum where possible, that's what it's talking about. Now, on the next one, when I want to find this infinite sum, my R value is in fact less than 1, so I can find that sum. This one is going to converge, so we can find the infinite sum. And the formula is really, really simple. It's just your a sub 1 and your 1 minus your R value. Now, I made this one have some fractions, so it's a little bit more work for us. So we're going to have our 10, and we're going to divide that by 1 minus this 1/7. Well, of course, 1 minus 1/7 is really 7 over 7. So what we're going to end up with here is 10 divided by 8/7. And we can jump that to a 10 over 1 times a 7 over 8. We can clean up those. Remember, we always need to reduce. We're going to have our 4, and we're going to get a nice, of course it might not feel nice to you, 35 over 4. Okay, so I tried to incorporate a whole bunch of fractions on these so that you guys could experience kind of as gross as they might be. But this is about as bad as it gets, and we'll do some more practice in class.